Welcome to our third and last thermodynamics video. We're going to be just tying up all the loose ends. So let's start off with a quick review on Hess's law, calculating the delta H for an unknown reaction the long way. It can be accurately estimated by finding a series of equations that, when added together, equal the one that you want. So you've done this before, where you say this equation and this equation, you add them together and you get a new equation, and you take their delta h's and you add those together and you get a new delta h. So you just need to remember that there is a multiplication rule as well as one that involves reversing the equation. If you multiply an equation by 2, then you're also going to multiply delta h by 2. If you reverse an equation, if you flip it, then you're going to change the sign. Be careful, this is different than with equilibrium. So if I switch the direction of a reaction, if I had delta H originally, and then I reverse the whole thing, it'll be negative delta H. If I take this equation and I multiply it times 2, then this will be 2 times delta H. So for example, I just wanted to look at that really fast. We have this equation that we're aiming for, and we know that N2 plus 2O2 reacts to form 2NO2. Use an arrow here. Let's use arrows. So I'm given these two equations here, but I want it to ultimately add up to this one, and we're trying to figure out the delta H of this one up here. So let's see. I know I want NO2 to be in the products, so I'm going to have to reverse this whole equation. And when I do that, this is going to become negative 112. I want 2NO2 in the products, and oh, that's what I've got, so I don't have to change that. Now looking at this other equation, it has 1/2 N2, but I don't want 1/2 N2, I want 1 whole N2. So I would need to multiply this whole thing times 2, which means this also needs to get multiplied times 2. So I'll have 180. So if you look at the next slide, it should, have the work for that. So we needed to reverse that equation. We needed to multiply the other one times 2. Then we'll take these new numbers, add them together, and you end up with 68 kilojoules. So this is Hess's law the long way. Hess's law the long way. Heat of formation, the standard heat of formation is the making of 1 mole of a compound by its elements at room conditions. There are other heats of, for example, there's heat of combustion, again, making 1 mole of a compound through combustion. There's a heat of ionization, making 1 mole of a compound through its ions, and then heat of reaction. So let's see here. If we want to figure out the enthalpy of a reaction, we have the shortcut, I guess, version, you could say, of Hess's law, which is the sum of the N. What's N? Moles. The sum of the moles of the products minus the sum of the moles of the reactants. And this number, these moles, these come from the balanced equation coefficients. So for instance, looking at this balanced equation here, we're going to take the products minus the reactants. Notice how there are 2 NO2s. So, excuse me, if you were to go into your textbook, I don't think these page numbers are quite right, but go in your textbook and you could find the different delta H's for different compounds and molecules, and you'd find for NO2 it is 34, and since there are 2 of them in the balanced equation, you get a 2 here. So those are our products minus Now this is all going to be reactants. And notice how it's both 0. That is because we have nitrogen in its natural state and oxygen in its natural state. You'll find that happens sometimes. However, that only happens with this equation with Hess's law. It's not going to happen when you do the bonds broken minus bonds formed equation. That will not show up in those equations. The calculation of delta S, which is also known as entropy, is exactly the same, which is always nice. It doesn't often happen. So same equation, just to replace the H with an S. And remember, this little degree symbol does not mean degree, it means standard conditions. Sorry, still recovering from my cold. Standard conditions, so that means what temperature, 25 degrees C, and what pressure, 1 atmosphere. It's also known as room temperature and pressure. Okay, so anyway, now we're going to calculate the entropy for the same equation. So the delta S for this reaction, you use the same coefficients from your balanced equation. You look up these numbers in a table. You do not have to memorize them. You get a number. This one came out in joules per mole, and it's negative. So does that make sense that it's negative? Well, let's think. Negative means that the entropy decreased as we went in this direction. We had less entropy. Less entropy. And that means less disorder. Is there less disorder as you go from N2 plus 2O2 to 2NO2? Well, we went from 3 moles of gas to 2 moles of gas. So yeah, you have less stuff, which, it's less mess, basically more order. So that sign does make sense. It's a quick check to make sure you're doing okay. All right. Another way to calculate delta S, the delta S of the surroundings is equal to the negative change in enthalpy over the temperature. And the sign of this will indicate the direction of the flow. So if you have an exothermic reaction, you're going to be adding entropy to the surroundings. And if it's endothermic, you would be losing energy from the surroundings, or losing entropy from the surroundings. You could test that out for yourself, plugging in positives and negatives for delta H to see how an exothermic versus an endothermic reaction affects your entropy of the surroundings. Remember, we're talking surroundings. So like if you have a reaction happening inside of a box, if it loses energy, it is going to the surroundings. Or other way around, it could be gaining energy from the surroundings. All right, something new. Calculation of Gibbs free energy at standard conditions. Hey, it's the same equation. Sweet. So you go into your table in the book and you look up your numbers, and oh, some of them are 0. That's nice. You get your coefficients from your balanced equation and you get a number. Now think back to the last video. I know for some of you that was before spring break. So is this reaction thermodynamically favored? In order to know, you have to look at the sign of delta G. So in this case, it is positive. And if it is positive, no, it's not thermodynamically favored process. It's not a thermodynamically favored process. It is non-spontaneous. Okay, there's another way to calculate delta G. This equation is given on your formula sheets, so you've got that going for you. You have your standard enthalpy minus your temperature times the entropy at standard conditions again. So you could calculate these a whole bunch of different ways. You could get your enthalpy from the Hess's law, like long version or shortcut. You can get entropy from using that equation that we just used, like the sum of n times the S, the products, minus, and so on, like we just did in the previous slides. Whatever you do, you find those numbers, you plug in your temperature, and you get a number for your delta G. So, what do you see about this number? What do you want to pay attention to when you are looking at your delta G? You want to pay attention to the sign. So in this case, it was positive. And let's analyze our enthalpy and our entropy. Our enthalpy is positive. So was this an endothermic or an exothermic process? Endothermic. And our entropy is negative. So this became more ordered. Lost entropy. And when you mixed those two things together, you ended up with a positive delta G. And is it thermodynamically favored? Heck no, it's not, because it's positive. All right, so now let's just kind of think about this. First, what would be the delta G at 400 degrees centigrade? So you calculate this delta G for some equation where you've looked up the numbers, whatever, you plug them in. 400 degrees centigrade. Well, I don't see a 400 in this equation. Where did that 400 factor in here? It's right here. They turned it into Kelvin. Degrees centigrade is the same thing as degrees Celsius. Okay, so they got 150 kilojoules per mole. Is this thermodynamically favorable right now? No, right now it's not because it's positive. Well, what if we compared it to the same reaction but at 25 degrees centigrade? So you've got to imagine then that right here, this is a much smaller number. Much, much smaller. So this whole chunk becomes a whole lot smaller. Now we were subtracting a negative either way, so it'll become positive. So instead of adding a really big number like 673 times 0.122, we'll be adding a much smaller number, 68 plus 25 times 273 times whatever. So if we're adding a much smaller number, is it going to be more or less likely to be thermodynamically favored? It would be more likely. Why would it be more likely? Because when we add a smaller number, so when adding a smaller number, the number is closer to 0, which is, closer to being negative. The delta G is closer to 0, which is closer to being negative. Okay, cool. So delta G and equilibrium. So we want to be able to relate Gibbs free energy to equilibrium. And remember, KEQ, what's the formula for figuring out an equilibrium constant again? It's either partial pressures or concentrations of the products over the concentrations of the reactants, or you could do the whole thing with partial pressures. Okay, so here's a definition. A system is at equilibrium when it is no longer able to do any work. In other words, when delta G is equal to 0, it is at equilibrium. This is something good to remember. Remember, though, although forward and reverse reactions continue to take place at equilibrium, there's no net change in concentration. So while we're still using up reactants and creating products, the concentrations aren't changing because it's going in the reverse direction at the same rate. Here is a new equation, which again I believe is on your formula sheet. You should double check that. Delta G standard is equal to negative RT times the natural log of the equilibrium constant. And then you could rearrange that, and you'd end up with this. Your delta G will come out in joules per mole, and that's because the R that you must use is in joules per mole Kelvin. Notice the Kelvin, your temperature must be in Kelvin, and your equilibrium constant, you must use partial pressures if they're gases, or molarity if they're aqueous, which, we did before. So now I'm going to introduce a few different cases so you could kind of see how delta G would relate to K. You could use it to predict your equilibrium value. So case number 1, you're given a Gibbs free energy of 0. And if that happens, then, the system is at equilibrium. Sweet. And equilibrium is not going to shift in any way because it's at equilibrium. It's done shifting. It's done. So you could say your KEQ should be equal to about 1 if your delta G is equal to 0. It's kind of a nice little trick. Here's another case. What if your delta G is less than 0? Remember, it's products minus reactants. So if it's less than 0, that means that you have less products than reactants. And it's right here, you could say, well, if it's not equal to 0, then it's not at equilibrium. And so it's actually going to shift towards the products to make more of them. Now, this all has to do with free energy. The free energy of your products is less than the free energy of your reactants, so equilibrium will shift towards your products to try to balance out those free energies. In a situation like this, you could predict that your equilibrium constant will be greater than 1 because of your free energy, we're going to have more products. Remember, lots of products, not very many reactants, gives you a number greater than 1. We have a name for this type of reaction. It's called exergonic. Exergonic. Exer. You could think exer is like exit. Products are towards the exit, so we're making more of the products. Whatever works. I'll review all of this in a minute. Let's just finish the last case. So here, the Gibbs free energy is greater than 0, which means the products had more free energy than the reactants, and that's not balanced. So in order to reach equilibrium, it's going to actually shift towards the reactants. Our equilibrium will have more reactants in order to balance out that energy. And if that's the case, we will have less products than our reactants, which gives us a number less than 1. That's why we could say our equilibrium constant will be less than 1. And this one's called endergonic. Endergonic. So let me just back up really quickly to that first one. So if your Gibbs free energy is equal to 0, the free energy of the reactants and the products are equal. It's at equilibrium. It's not going to make more products than reactants. They should be pretty equal. So our equilibrium will be equal to 1, our equilibrium expression. However, if there is more energy in the reactants than in the products, the equilibrium will shift towards the products. We will have more products, which will give us a greater than 1 equilibrium constant. And if the free energy of the products is greater than that of the reactants, to balance that out, equilibrium will shift towards the reactants, towards the left, which gives us an equilibrium constant less than 1. So here it is again. If this sort of thing helps you, you could look at it. It's a way to estimate your equilibrium constant. So if your delta G is greater than 0, it's going to be mostly reactants. However, once you get past 20 kilojoules, those colors are very close. I did not mean to do that. Then it's basically all reactants. Virtually entirely reactants once you get past that threshold. If you have a delta G that's less than 0, then it's mostly products. But then once it gets less than negative 20 kilojoules, then it's virtually entirely products. What I would suggest doing is figuring out how to reason your way to this and this. So that way all you have to memorize are the numbers positive and negative 20. So what if the conditions aren't standard? What do you do? Because for all of these we've been assuming it's standard. So delta G, it has a tendency to go towards the products. And the more negative something is, the more likely it will be for it to go towards the products. It's more thermodynamically favorable to go towards the products. So, I mean, you could use this equation here to help you out with calculating delta G at different temperatures. Makes it pretty easy, actually. You take your standard conditions, delta G, you're going to convert it. You're going to use your R, the same one as before. Get used to using that R value. You use temperature still in Kelvin. And you're using the natural log of Q. Remember what Q is? It's very similar to K. It's like K. However, it's not necessarily at equilibrium. Not necessarily at equilibrium. So this is a cool little equation that allows you to convert your delta G at standard conditions to your delta G at, other conditions. So here is a example problem. Predict which way the equilibrium will shift for a reaction mixture at 25 degrees Celsius. Sorry, let me get that. At 25 degrees Celsius, that consists of 1 atmosphere of nitrogen, 3 atmospheres of hydrogen, and 0.5 atmospheres of ammonia. So first we're going to calculate our delta G standard. Now we know, okay, this is at standard temperature, but we don't necessarily know that it's at standard pressure. So what we need to do is say, okay, delta G standard is equal to delta H standard minus T delta S standard. And they gave us those numbers. That's nice. We don't have to calculate it all out. 38 minus T 298 times delta S, negative 198.3. And let me plug that in. We'll see what we get. Negative 1, oops. Oops. I'm using a different calculator than usual. It's messing me up. 92.38 minus 298 times negative 198.3 equals. Okay, so, ooh, that's a big number. 59001.02. Okay, this is our delta G standard. You know what I just realized? Here, learning experience for you and me. Look at this delta S. What units is it in? Joules. It's in joules per K. Joules per K. Well, that makes sense, I guess, because if I cancel out the temperature from here, that leaves me with joules. Okay, good. I'm not freaking out, but I need it to be in kilojoules so it matches my delta H. So let's change that. This is actually going to need to be negative 0.198. Okay, let's just get rid of this 0.1983. All right, let's try that just one more time. So negative 92. Negative 92. Oh my gosh, wow, negative 92.38 minus 298 times negative 0.1983 equals, aha, I like this number. Okay, 33.29 in kilojoules per mole. Okay, so this is our delta G standard. However, we want just plain old delta G. So remember, let's see, where is that slide? It's right there. There's our equation we're going to use. RT, natural log of Q. So delta G equals delta G standard, so 33.29. However, RT, natural log of Q. R is in joules per mole Kelvin. So I probably want my delta G standard to be in joules per mole Kelvin. So let's change that. 33290. Now it's in joules per mole, so it'll match my R, plus R times T times the natural log of Q. That's what I'm going to plug in here. Q. So Q is product over reactants. So product right here, there it is, NH3, ammonia, 0.50, but remember it's squared from the balanced equation over my reactants. So let's see, 1 for nitrogen, and hydrogen is 3, but that's cubed. So that number divided by 3 cubed, 3 times 3 is 9, times 3 is 27. I'm not using a scientific calculator, so. All right, so here's my Q, 9.26 times 10 to the negative third. I'll plug that in. 9.26 times 10 to the negative third. Okay, now if I plug and chug all of that, I end up with a delta G of negative 46 kilojoules per mole. All right, and with that number, we could say, all right, it's negative. It's negative. My delta G is negative. It's going to be shifting towards the products. We're going to be needing to make more products in order to balance out the lack of free energy coming from the products, which means it'll make more ammonia. Cool. All right. You should probably go back and practice that problem without me sometime. I will give you problems in class too. Okay, last question, or slide. This will just review the 3 different laws of thermodynamics that you need to know. First law states, that energy is conserved. Simple as that. All energy has to end up somewhere, either in its original form or a different form. It doesn't have to be heat energy. It could be something else, but it is constant. The second law states that the disorder in the universe always increases. Entropy always increases. After cleaning your room, it always has a tendency to become messy again. This is a result of the second law. As the disorder in the universe increases, the energy is transformed into less usable forms. Thus, the efficiency of any process will always be less than 100%. That's pretty sad. All right, third law. All molecular movement stops at a temperature we call absolute zero, or 0 Kelvin. You've learned about this many times, but you probably haven't seen it in the form of a law. So there's the law. All molecular movement stops at absolute zero, theoretically. Since temperature is a measure of molecular movement, there can be no temperature lower than absolute zero. At this temperature, a perfect crystal has no disorder. Ooh, no disorder. All right, there you go. That is the end of our thermodynamics unit. So now it is time to practice, 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 practice. See you later.